Essentially, it's the application or applying math techniques to describe chemical process. In developing this from an academic standpoint, we'll do this in the same format that we have been developing all along relative to the Dalton's atomic theory. We want to talk about the mathematics as it applies to elements. In that context of problems and so forth. We've done some in conversions. You've seen that. And of course, apply from there to molecules and compounds. How do we describe molecules? What's the most common way to talk about molecules in a quantitative format? And chemical reactions. Our work so far has involved identifying classifications and placing the different kinds of reactions in various categories, pigeonholing on things of that nature. But in this section, the mathematics that we apply to all of those classifications, every one of them. So when you learn the techniques here, you can apply them to all of the classes and types of reactions that you're essentially learning about right now. Now, to begin this, we want to start with a subject that you are already familiar with, and that's formula weight. So in a typical periodic table, we will be using the formula weights, and we'll be adding those numbers together. And when we get an outcome, we will call it atomic mass units. Now that will evolve into another term, gram molecular weight, grams per mole, and those kind of things, so to give you an idea where we're going. Also, in the use of these numbers, let's see if I can get a bigger spread here. There we go. You will see the accuracy of the number, precision of the numbers goes out in some cases 4 digits to the right of the decimal. Now, how do you know how far to carry it out? Well, that's a sig-fig problem right there. So if you're working in a practical environment and need to maintain accuracy within certain parallel limits or specific limits, then you want to determine how many digits you need to retain in working out your formula weights and things. Me, in working problems on the average, I'll round them to the nearest whole number and add them together. Oxygen's 15.9994. I'm going to round it to 16 and keep going. Added 32 for sulfur and 24 for magnesium, and round them off and get a number and apply it to the problem. How do you figure out what you need to do on the test day, which is in many cases the most important thing to you right now? Look at the answer choices. They'll tell you how many digits to round off to, and everything will work out fine right there. So just a little hint for the wearing. So as you are familiar, we will start with a couple of simple, and this maybe I'm assuming wrong. I'm going to work some simple formula weights and some molecules and formula weights, and let me get this thing back to where it's supposed to be. See what's going on. Okay, so water, of course, is H2O, and if we need the formula weight, is equal to sum of all the atomic weights. and that translates to be atomic weights of 2 hydrogen atoms and atomic weight of 1 oxygen atom. In a periodic table, hydrogen is listed as 1.00794 atomic mass units. So we have 2 times 1.00794 AMUs. And AMU are atomic mass units. Okay? That is added to 1 oxygen weight, and so on the periodic table we find oxygen listed at 15.9994 atomic mass units. So that would be 1 times 15.9994 AMUs. If you need that kind of accuracy, fine. Extend it to those number of decimals to the right of in the atomic mass. For purposes of expediency and efficiency and trying to get through everything, I round them to the nearest whole numbers. So hydrogen will be essentially 1. Oxygen will be essentially 16. And the outcome will be in atomic mass units. And we'll see that is 18 atomic mass units for the formula weight. And I will designate that F dot WT like that many times to save time. And when I'm scribbling along Mach 2, then and do that, you'll understand I'm talking about formula weight from the periodic table. Let's look at multiple elements in a compound like this. As you look at the formula, you see it has 3 elements, so its formula weight will be the sum of the atomic weights of 1 sodium plus 1 oxygen plus 1 hydrogen. And as indicated, I intend to round things up for expediency purposes. The value on the periodic chart that I have for you, we've used 22.9898. Well, I'm just going to put 23 for oxygen, and that's atomic mass units. For oxygen again, 16. And for hydrogen, 1 AMU, like that. So we find it has a 40 atomic mass unit value. Sometimes parentheses are used in writing formulas to isolate a polyion against a cation and to prevent subscripts meaning too many elements of one kind or another. Ammonium phosphate. Requires that we put a parenthesis around the ammonium ion, subscript 3, to compensate for the -3 charge on phosphate ion. And if we have to calculate the formula weight, we have to take the 3 and apply to everything inside the parentheses. So in this relation, formula weight would be based upon 3 nitrogen elements, 12 hydrogen atoms, 1 phosphorus and 4 oxygens. adding them together or substituting the atomic mass values at 14 plus 12 times 1 1 times 31 plus 4 times 16 NAMUs. Oh, that's better. Only one other that I think requires comment at this point. Hydrates. We worked with a substance in the lab, sent water and hydrate, and copper sulfate pentahydrate would be represented in this format. This shows coordinated water, 5 molecules of water coordinated. Water in itself, as we shown earlier, is 18 atomic mass units, and so when I have to deal with something that's coordinated like that, 5 waters, I go 5 times 18 and use it as a grouping. So the formula weight here would be copper plus sulfur plus 4 oxygens plus 5 H2Os. You see the copper is 64 atomic mass units, 32 for sulfur, 16 for oxygen, and 18 for water. And that will be in atomic mass units, giving us 64 plus 32, 64, and 9 atomic mass units. 250 atomic mass units, the sum on that. So many problems in your future will start with in context like this. You'll find yourselves in the future, when you're very comfortable working certain problems, scribbling out the weights in the border of the page that you're working on just to get the formula weight. Some people actually have tables, 15, 20 pages worth of tables, and they just look them up. They've already been calculated. In chemistry, probably the most important issue is how we express mass values relative to chemical substances in terms of elements and compounds, and that evolves from an issue called the mole concept. The mole is a weight unit in context of the chemistry. I've attended lectures where professors have gone off on these large discussions of MOLE, animals, and odd and end stuff. That's not necessary, in my opinion. Maybe it is. I don't know. I'm going to tell you what it is, and we're going to use it. That's the long. A mole in chemistry is 1 mole is the mass. Formula weights, okay, of substance containing 1 Avogadro's number of particles. That is, Avogadro's number, which is usually script N or capital N with a subscript 0, as I'm showing you here, is equal to 6.02 times 10 to the 23rd units, particles, items, however you wish to look at it. If we're talking about 1 mole of any element, we're talking about 6.02 times 10 to the 23rd atoms of that element. 1 mole of hydrogen is equal to 6.02 times 10 to the 23rd hydrogen atoms. And it turns out that 1 mole of hydrogen is the formula weight. The formula weight of any substance, whether it be a compound or an element, expressed in grams, is the mass of substance containing 1 Avogadro's number of particles. This is referred to as a gram formula weight. So if we're asked to calculate the weight of 1 mole of silver chloride, it would be the formula weight. So 1 mole silver chloride is equal to 1 formula weight, which is equal to the sum of the elements, which in this particular case is 107 or 108. Let's do 108. Excuse me. Plus 35. And in this case, it is expressed as grams per mole. The essence of this concept is to convert mass into moles, or moles back into mass. Divide by formula weight. If you are given 36.8 grams of sodium chloride, how many moles does this represent? The simplest issue is multiply grams times the formula weight of sodium chloride. So the moles now NaCl are simply 36.8 grams, which is the specification that you are working with, divided by a formula weight of 58 grams per mole. Notice the denominator units are fractional. You invert and multiply, grams will cancel out. End up with 6.35 moles of sodium chloride. Incorrect, I'm sorry about that. Anyway, divide by 58.634 moles of the sodium chloride. It's in your moment. On the other side of the fence, we find you might need to convert moles back to grams. Well, the process is multiply by formula weights. Assume you're given 0.0245 mole of O2 gas. Calculate grams of O2 gas. Well, the process is simply formula weight of O2 is 2 times 16 grams per mole, which is equal to 32 grams per mole, and then the grams O2 now is 0.0245 mole O2 times 32 grams per mole O2, if you want to keep the units consistent. Moles O2 cancel out, and the outcome, of course, is in 0.784 grams of O2. So raise it up a little bit so you can see like that. You need to know to do this intuitively, reflexively, without thinking. As you look at a problem, the issue will be an equation, and you'll be given mass values relative to the substances in that equation, and the rule will be convert to moles, solve the problem, and then convert back to grams for whatever reason the problem would have. When I say intuitively or reflexively, that is, and you don't have to answer this, if I ask you what your name is, you'll tell me. You don't have to think about it. So converting mass to moles divided by formula weight, or moles to mass multiplied by formula weight, it's just one of those things that you're going to do so much from here to the end of this course. And if you stay in any chemistry field, analytical chemistry field, this is going to be a dominant dimension of what you are and will be doing. So in essence, that's the long and the short of the fundamentals of the mole concept. Giving you a mass and you need it in moles, you divide by formula weight, or multiply moles by formula weight and you get it back to grams for whatever issue you might. The biggest issue in mole concept is applying it to the chemical equation. Okay, so just a brief outline of this, then we'll drop back and then we'll apply some things to issue in chemical formulas like determining empirical mass and bonding ratios. I sent everybody a note on what you should have gotten in the magnesium oxide, and those are theoretical numbers I calculated, but they are based on the formation of magnesium oxide in a 1-to-1 ratio. So we'll get to that. Okay. This topic is application of mole concepts to chemical equations. Or reactions. the question we have for you up front is how to read the equation in terms of moles. If I were to give you the following equation, 3H2 in gas plus N2 in gas form produces 2NH3 in gas form. Question is, what do you see in terms of quantitative issues? What can you derive out of this equation? A number of issues can be extracted from this, and it's absolutely critical that you understand this at this point, in that future work will assume you already know this and can apply it so that we can stack it higher and deeper, so to speak. First thing that you can extract from a chemical equation is moles. Mole quantity. How many moles of molecular hydrogen? How many moles of nitrogen? How many moles of ammonia represented in this equation? The coefficients of the balanced molecular equation will tell you that. So if you look at the coefficient of molecular hydrogen, we're talking about 3 moles of hydrogen, molecular hydrogen gas. 1 mole of molecular nitrogen and 2 moles of ammonia. Now, the second thing you can extract from this is mass numbers, and I call it equation mass. So as not to confuse the mass of a mole or formula weight relative to that equation. Now, it's all tangled up in there, but it can get confusing. 3, if you know that by looking at the equation, the 3 means moles, that's also 3 formula weights. So coming down here, I'll put it right down here for this one. 3 formula weights of H2. Well, of course, that's equal to 3 times 2, 1 for each hydrogen, that's 2, grams. That is 6 grams. That is the equation weight in that equation. If I'm interested in the mass values for nitrogen, grams of N2, that was H2 gas there, so gas right there, I would have this equal to 1 times the formula weight of molecular nitrogen, which in essence is 1. 14, 14 is 28 because you have subscript 2. And you tag that with grams and it's 28 grams. This is the equation weight of nitrogen. And then finally the mass ammonia. Mass in grams, sorry. Gas is 2 formula weights of NH3 gas, which is 14 and 3, 17 grams. This is the equation weight of NH3 in that expression. You can also obtain what is called particle numbers in relationship to Avogadro's number. Particle numbers related to Avogadro's number are just the coefficient times Avogadro's number. So if you're interested in the real number of particles based on the equation, this is 3 moles, and 1 mole is Avogadro's number, then 3 times Avogadro's number. So in this, the number of particles of H2, not N2, sorry, number of particles of H2 gas is equal to 3 times Avogadro's number of particles of H2 gas. And that, of course, is 3 times 6.02 times 10 to the 23rd H2 gas molecules. Now, why you would need it is dependent on the circumstances you're working in, problem or whatever. But you know that's one of the issues that can be extracted from the equation. Now, particles of N2 gas is, of course, 1 times Avogadro's number, which, of course, is 6.02 times 10 to the 23rd N2 molecules. Finally, round this out, the particles of ammonia gas is, of course, 2 moles in the expression, 2 times Avogadro's number, or simply, I'll just write it out, 2 times 6.02 times 10 to the 23rd ammonia molecules, NH3. Also from the chemical equation, again, you can get gas volumes and energy numbers. If we're talking about gas volumes, the issue is called molar volumes. That's the expression or terms. Typically, you'll see me abbreviate that V with the subscript M, molar volume. 1 molar volume is the volume occupied by 1 mole of any gas. The equation we're using, I like this one because all of the coefficients are different. The ammonia, 3H2 gas plus N2 gas. I'm telling you, I'm making a mess. N2 gas goes to ammonia. Gas. And in terms of gas volumes, the issue is expressed in terms of molar volumes. And so we look at the equation, while this is 3 moles, looking at the coefficient, the volume is 3 molar volumes. and N is 1 molar volume, and ammonia is, or nitrogen is 1 molar, and ammonia is 2 molar volumes. When you look at an equation that's written without anything else but the balanced equation and maybe state of existence, you assume that is at standard conditions of 0 degrees Celsius and 1 atmosphere. If it is not at 0 degrees, the author or the publisher of the equation for the conditions and research he's doing will have to specify temperature and pressure for the work he's doing, because any calculations that are extracted from it would be incorrect, because you will enter the problem thinking, well, if he doesn't put anything, it's going to be 0 degrees. And for example, at 0 degrees, I'm going to put it down here, give yourself a little space. At 0 degrees Celsius and 1 atmosphere, 1 VM equals 22.4 liters for any gas on the planet. 22.4. So if I write the equation without specifying a temperature conditions, and you need to determine the literal liter volume of it, then you would be impelled to come in at 3 times 22.4 liters. 1 times 22.4 liters for the molecular nitrogen, and 2 times 22.4 liters for ammonia at STP is what it's called, standard temperature pressure conditions. So when we talk about what can you extract from an equation, what have I given you so far? Well, moles, look at the coefficients. Mass, look at the coefficients times formula weight, equation mass. Number of particles, coefficient times Avogadro's number. And gas volumes, coefficient times a molar volume. But the molar volume is dependent on temperature pressure issues. If nothing's written, you assume 0 and 1 atmosphere. The last thing, okay, so if you double the quantities, you can see here I've doubled, then you'll have to double the heat quantity. If you divide the quantities in half relative to the original equation, you will have to divide the energy number in halves. Or 1. So this means you can scale it up or scale it down relative to what energy is delivered from or into the reaction system. The last thing is I need to be able to take solution data and convert it to moles. Because in real world problems, this is called a titration. And to be able to take titration data and convert it to moles of one or the other components, you can apply it to the equation, set up your ratios, and determine unknowns in this context. And the world is not just black and white equations on paper. But this now becomes the titration of one component into. In this example, you can see it on the demo table. I have a burette, which contains a chemical here, and so forth. And down here, I have another chemical. Well, as I've got this set up, the sodium hydroxide is in the burette. And in the beaker, I've got hydrochloric acid. When I mix them together, we're going to make salt and water. Can you see the blue dots and the red dots down here? Now watch what I do very carefully here, and you will learn something that will carry with you forever. The red dots are the HCl, and the blue dots are the base, NaOH. What's the reaction ratio here? 1 to 1. If I look at the equation here, okay, what do I have here? I have 1 mole of HCl and 1 mole of NaOH, and that's going to produce 1 mole of sodium chloride and 1 mole of water as a driving force. That's the standard equation. I double it, I get twice, everything doubles. If I cut it in half, everything cuts in half. So we know this. But how do you translate it to this? What I'm going to do is I'm going to take a quantity of this in terms of a volume, of this, along with the concentration. See, I know how many particles I have per unit volume, and against however many down here I neutralize, and I can figure out what I use. Now the volume down here is known, and this is the volume used. Okay. You will have in the burette up here is a solution of known concentration. And down here you will have a solution of unknown concentration. Okay, you've got a volume and a concentration number. A volume and a concentration number. Now I'm going to tell you how to take that data. You're going to add volume, so many milliliters. Or let's do it in liters. And convert it to moles. Well, it turns out that when you add this stuff in, knowing what the concentration, okay? Moles added is equal to molarity times the volume added. Molarity times volume is moles. Molarity times volume is moles. You need to get used to that real quick. So what I'm going to do is I'm going to run this reaction to neutral. And when I reach neutral, I will know I will have consumed all of the red dots. See, the acid is the red dots. When all the red dots are gone, I'm neutral. All I'll have in the solution is salt. So when I add a blue dot to the red dot, it's going to change into salt. And I'll keep dropping blue dots in until I have 5 purple dots, which I'm going to use purple here in a minute. Okay? Now, here in this case, base completely reacts with all acid in beaker. So really there's no acid or base remaining, and there's only salt. So if you know how much base you put in, you can calculate how much acid. Okay. This real quick. See if you can put some numbers into this. Okay. So this is some magnesium. And essentially you have a beaker which contains a quantity of HCl. And you're going to be throwing some solid magnesium in there, in powder form or whatever. Okay, so when you throw the 0.3 mole of magnesium in here, how many moles of the HCl did you react with in here? Is the question. Well, you look at your equation, and the equation says you're in a 2-to-1 reaction ratio. For every 1 mole that you drop in, you react with 2 moles of HCl. So we didn't add 1 mole, but we added a 0.3 mole. The equation says the HCl that I will react with from this amount is twice, just like this. That's a simple linear ratio. 1 mole will react, that's the way I write it, with 2 moles of HCl. Question is, how many moles of magnesium, how many moles of HCl, will you react with 0.3 moles? And this is what I mean by relating it back to the standard equation. See, this is given, and it's always a known. And when you put one of the components in, and you find the moles of that one, you can get the moles of the other one. And from this, you get 1 mole magnesium, 0.3 mole magnesium is equal to 2 moles HCl over X. X is your unknown. You see how that's linear ratios. And so cross multiply and solve for X. X times 1 mole magnesium is equal to 0.30 mole magnesium times 2 mole 0.6, 2 moles, that's right, 2 moles of HCl. Duh. Okay, let me move this up a little bit here. Okay, solving for X, I have 0.3 mole of magnesium times 2 moles of HCl divided by 1 mole of magnesium. So moles of magnesium drops out, and the only units I'm left with is moles of HCl, which is 0.3 times 2 moles HCl that you reacted with, or 0.6. And so that's what I'm trying to tell you. It's proportional. And we can relate that back to the equation, just like if you're working in moles. Okay? There's your equation. Now just look at the equation. Let's talk about that for a second. What can you derive out of the equation in terms of moles of each component, just from the equation? Okay, what is this? 1 mole? Everybody okay? All right, now stop me if you need to. 1 mole of that compound, assuming the equation's balanced. Yes? Any questions? How many moles of sodium chloride do I have? Anybody? Come on, that's right, 2. So we got 2 moles. Okay, and on this product side, how much sodium nitrate did I produce? What does it say? 2 moles, okay? And how many moles of lead chloride? How many? 1, okay. I want y'all to understand this. Now, somebody like me, mean, angry, and awful, comes up and gives you a problem and said you're given 315 grams of that lead nitrate, and you're going to add it into a solution of sodium chloride, which contains more than you'll need. Now, you're not going to react with more than you need. That is, you're only going to react with 1 to 2 ratio. I don't care how much you have. You'll have just excess left over. Okay? So I'm just going to put excess right here. What I want to know is how many grams of lead chloride are you going to get out of this? Are you going to get out of this reaction?
Good.
The rule that I preach over and over and over and over is convert the given data to moles. Apply to the equation in linear ratio and convert back to anything else they want you to have. In this case, it'll be grams. So we can use this data between here and here if we go to moles that we put in there. Okay? Now, moles, as you recall, is the mass given in grams divided by the formula weight of the compound of interest. So we're given 315 grams of the lead nitrate. Yes? See that? We have to divide by the formula weight of lead nitrate. So I'm going to come down here, formula weight PbNO32 is lead plus 2 nitrogens plus 6 oxygens. And lead, okay, it gives us, so we compute formula weight is 331 grams when we add up all the atomic weights. So we need to now come up here and divide this by 331 grams per mole to get the moles of lead nitrate used. Okay? So having that, and everybody know how we got here. Okay? Mass given divided by formula weight gives us the moles used. 952 mole here. Well, look at the equation that's balanced. Well, if I use 1 mole here in an excess, I'm going to get how much if I use 1 mole? The same amount. So if I use 0.952 mole, how much am I going to get here? Same amount, right? Everybody good?
Yes.
Okay. 0.952 mole. That's what the equation says. 1 to 1, 1 to 1, same, same. That's what it means. Same and same. The question is, how many grams? So all we have to do is convert this to grams by multiplying by what? Formula weight. So acting the problem, I get 263. Is that what y'all got? Yeah. The issue is convert to moles. Apply to the equation and then convert back to whatever the problem's asking you. what's the equation in here? HCl, I could have used HBr, in the HCl aqueous plus NaOH. Double replacement reaction, acid base, goes to what? NaCl plus H2O. Okay? Now what does the problem say? I have 25 milliliter to 0.1 molar HCl. So I write that 25 milliliters and I'm putting 0.1 molar right there of HCl. Here is 30 milliliters of 0.12 molar sodium hydroxide. How do I convert solution data to moles? Bingo. Says, you can't read that, we'll use only 0.025 of the sodium hydroxide. The equation says so. 1 to 1. The one in the lowest amount is called a limiting reagent. And we'll work the problem with that. But the issue that's more important is when you converted it to moles, it was easier to see through the problem. If I left it in solution data, it's not real obvious. That's the issue. So molarity times volume gives you numbers that you can compare to the equation. Is everybody comfortable with the idea that sodium hydroxide is in excess?
Yes.
Based on the equation up here? Well, it doesn't get any harder than that. Now they may ask you how many grams or something like that, but what's the pH after the thing's finished? You have to take the difference between 36.36 and 0.0036 and 0.025, which gives you the constant moles, and then you divide by the liters of solution and apply it to an equation for pH and stuff like that.